In this video, we will be talking about the gradient descent method to find the local optimum points of a given function, multivariate function. So for instance, if you consider the function f of, say, xy, and our function will be, say, defined by 5x squared plus, say, for instance, 3y squared. Our goal is to find the global minimum. So this function doesn't have a maximum, but it has a minimum, and it's very easy to guess what that minimum will be because x squared, squares are always positive, and y squared, they're both positive. This expression is always greater than or equal to 0, so it's not too hard to see that this function has a minimum, which turns out to be a global minimum, by the way, at xy equals 0, 0. So when you plug in these values, the minimum value will be 5 times 0 squared plus 3 times 0 squared. That's equal to 0. Any other value for x and y that you put will be greater than 0. As an example, if you plug in -1, say 0, for instance, 5 times -1 squared plus 3 times 0 squared. -1 squared is a 1, 5. So this one will give you 5 plus 0, which is just a 5. Or you try something else, let's say 1/2, 1/2. So that would be 5 times 1/2 squared plus 3 times 1/2 squared. 1/2 squared is just 1/4, so we have 5/4 plus 3/4, and that's a 2, again strictly greater than 0. So we can imagine that indeed 0 will be the minimum value of this function. And now let's figure out a new method, so something called the gradient descent method, to understand the a very nice method to recursively find this minimum. And so what I will do is, let me just go ahead and draw a graph on the coordinate plane xy. Now the thing is, because this is a multivariate function, the values takes place on the third dimension, the z direction, which obviously it's impossible for me to draw. As a result, what we will come up with will be contours, level curves. So let me just give you an example. So consider this function, which so these are the contours, something like that. And suppose that our goal is to find, you can think of, if you've seen maps before, these are all the points that have the same height. Any 2 points on a contour, for instance this point here A and this point here, because they are on the same contour, they are the same height, and they are both higher ground than this point C. Does that make sense? So the z value for A and B, the function, if you were to evaluate it at the point A, which have coordinates xa, ya, and similarly this one has xb, yb, and this one is xc, yc. So what happens is, if you were to plug in to the function the point xa, ya, you would see that it would be equal to xb, yb if you were to plugging in the point xb, yb. However, these two numbers would have been strictly greater than if you were to plug in the value xc, yc. Does that make sense? So the goal is to find the minimum value, and because each of these level curves are such that the one at the very bottom is somewhere here, right? So this one. So the minimum point would be inside that. So for instance, just as an example, suppose that the z value here is, let me write it in a different color. So suppose that this is the level curve where z is equal to, say, 10. This one is the level curve where z is equal to 9, z is equal to 8. This one is the level curve where z is equal to 7. And this one is also z is equal to 7, right? This one is the level curve where z is equal to 6. This one is also z is equal to 6. Sorry for that. And finally, this last one, this is z is equal to 7. Do you guys see that? So our goal is to go down. Oh, sorry, not 7. I meant to say 5. lower level. Okay, so the global minimum will end up being here. There's another, oops, sorry for that. So somewhere inside this, let me just go ahead and use a different color here, yellow for instance, this yellow part. It has a minimum here. It has another minimum inside this region, but somewhere inside. You can think of it like, if you've seen a geography map, like the mountain tops, or in this case, it would be like the bottom of the ocean. So there's a bottom of the ocean somewhere here. There's also another bottom here, and this bottom is lower than that bottom. The same method would apply for finding the mountaintop as well. So instead of calling it gradient descent, we will call it the gradient ascent method, and the method works also for that case. So how does the method works? So the method works as follows. So you start with any random point on where? On any of the contours. So say suppose for instance that we start with the point, I don't know, let's start with this point. Let's call this point x sub 0. Well, actually, because it's in the two-dimensional, so let's call it x0, y0. There you go. So if you start with this input, the method says the following. Find the tangent line to that contour at that point, which is something like this, and then we will find something called a gradient, which is a perpendicular. So we will find a perpendicular line to that gradient line, and so what we will do is that perpendicular line, which we call it as the gradient, and that's the name where the name comes from, the gradient descent, right? So so along this gradient line, we need to find a contour which is tangent to that line, which is this invisible contour here. There are infinitely many contour lines, so this is the point, and at that point, so that will be our next point in the recursion basically. So let me make it bigger. So this point will be x1, y1, and then from there we will draw a new gradient, which will end up being draw a perpendicular. Oops. So maybe I should do a better job here. Okay, let's do it again. Oh, there we go. There we go. So this is a 90-degree angle. And then again, just keep drawing the gradient lines until you find the one which is tangent. So pretend it's somewhere right here. All right. So our new point is here. Right here. And then from that point, just keep drawing perpendicular lines. Does that make sense? So you keep drawing perpendiculars until you reach to that mountaintop, or in this case, the bottom of the ocean. In this case, sometimes the steps will get smaller and smaller, as you can imagine. So, but ultimately at infinity, we will reach our destination. There's a very tiny point over there. It's hard to visualize it, and I won't even bother visualizing at this step. So what I will do is, let me just show you how a typical path will look like. Maybe I can draw a different color, let's say pink color for instance. So we're starting at this point, oops, that's too thick. Okay, there we go. So we walk through here until we reach that tangency, then down to here, then down to here, and then down. So it will gradually move towards closer and closer and closer to that optimum. Interestingly, depending on the starting point, if we started somewhere, let's say closer here, we could have had a path which would have been so probably after I draw the tangent, this 90 degree, I would have hit here, after which I drew a new tangent, so I go this way and then I go that way. So in that case we would hit another a minimum point. Does that make sense? So the whole idea then is to be able to draw these tangent points. So let me just go ahead and show you the equation for those tangent points, and then we can move on from there. Basically, we will do most of the work on Excel. So that will be the idea. But okay, so the tangent line is the follows. And then rather than the tangent line, the perpendicular line to the tangent line, right? So this line, the one that we mentioned earlier, the gradient line. Gradient line, let me write that down. Gradient line is perpendicular to, well, it's perpendicular to the contours for are for a particular value f of x0, y0 to that starting point. And the gradient line has the following feature. We usually show the slope of that gradient line with that inverted triangle f, and it is simply taking the derivative of our function with respect to x, and then comma the derivative of this function, our function, with respect to y. So that is the direction, all right, is the direction of the gradient line. So once we have the direction of the gradient line, life is pretty easy. It is very easy to figure out that path. But the problem now is, where do we stop? How do we know the value of x1, y1? So for that, we will do the following. So first of all, our starting point is x0, y0. And to that pair of x0, y0, I'm going to represent it like this, in vector form, rather than like this. They are the same thing, basically. x0, y0 like this. Instead of showing it like this, I'm going to show it as a 2x1 vector, and it will be the following, or even better, x1, y1, the next point, right? So that's the point that we want to reach. x1, y1 will be such that you will start with points x0 and y0, and then we will go a certain distance, say d, for instance. We need to choose a distance d to walk along that direction. So once we decide the direction, we're still not done, right? So we need to figure out how far along that direction we need to walk, d. And then once we have the next gradient, we need to figure out the next one, so d1, d2. So how far we need to walk, so we will identify that next. So d times, and then the gradient, which is df over dx, and then df over dy, but I should have been more specific here, evaluated at x0, y0. All right, so these values, maybe I should have written that like that, evaluated at x0, y0. There you go. I think the best way would be to, and then based on that, find an optimal one. Find optimal walk. When we say find optimal walk, the optimal walk such that the function z is equal to f of xy will be minimized. Does that make sense? So basically, you can, as an example, consider this is a map, and you're inside that map, you want to find the bottom of like in a geographical map, where these contours are, these curves are basically the heights, and you are at that point by the mountainside, and you want to find the bottom, the point with the smallest altitude. So I think it makes common sense that you will first try to go as steepest as possible, find the direction where you go downhill, and then stop at the point after which you no longer walk downhill. Again, instead, if you were to pass that point x1, y1, you would have been climbing up the hill again, right? So this is the point with the slope. So in that direction, the smallest distance, right? If I take a cross section, you can imagine it like this, a cross section. Let me give you an example of that. So the cross section will look like this. Once we find the direction, so it will look like this. It's as if we are walking down a hill, and after which it will go up again. So that point here is our point x1, y1, our starting point, x0, y0, I should say. And along that path, we need to go all the way down to that point, x1, y1. x1, y1 is such that the value of the function f of xy is minimized, right? And we want to stop there. So this distance is the distance that we are seeking. All right, so this is the distance d1 that we need to figure. Okay, let me write it d1. I think the best way would be directly to work with our example. So at the beginning of the problem, I gave you this example. So let's directly work with this example. And so let's have a starting point. Suppose that we decided to start at the point 4, 4. All right. So starting from the point 4, 4, let's see the direction where we can go and so on. So let me rewrite our function. Z is equal to f of xy, which is, hold on, it was 5x squared plus 3y squared. 5x squared plus 3y squared. Pretty much to begin with, we need to find the derivative of the function f with respect to x. What that means is we are taking partial differentiation, and so we are just assuming under those circumstances that y is just a constant. So just the only variable is x. When you take the derivative of this portion, it's just 10x. And we've done it before, and the second part is just a 0. Similarly, if you were to take the derivative of the function with respect to y, that would have been 6y, because you should treat x as a constant. If you check textbooks, they will show the letter D for differentiation. They will write it in curly font like that. What it means is they are recognizing that the function f is multivariate. It has two inputs, and so that's why they put that, but it's basically the same purpose. All right, so like we said earlier, we want to calculate this, the value of del f over del x, the partial differentiation, partial derivative of the function f with respect to x at the point x0, y0, right, at the starting point. So that's 10 times, x0 was 4, or we decided to start at the point x0, y0 equals, say, 4, 4, right? And so 10 times 4, and that's a 40. And similarly for, so this implies del f over del y, the partial derivative at the point 4, 4. Okay, let's just write 4, 4, I guess. That's the point we're evaluating it at. So it would be 6 times 4 again, and that is, actually, you know what, let's just start 4, 5, why not? Because otherwise it's confusing, right? So 4, 5. There you go. 6 times 5, and that's a 30. There you go. All right, now we're ready to find our points, the coordinates of our points x1 and y1. So for x1, we will start with x0. X0 is just a 4, or let me write it in 2 steps. X0 plus d1x, or let's just call it, d1x times, or actually this is just d, right? So d1 is just a constant, sorry for that. d1 times the gradient, which is 40. Does that make sense? Or let's just write it as gradient, and then in the next step we can, all right, there you go. Evaluated at the point x0, y0, oops, x0, y0, all right? And then we'll do the same thing here. d1 times the partial derivative of the function f, evaluated at that point again. All right, so x0 is just a 4, plus d1 is the unknown, times, because we still are at that point, we figured the direction, we calculated the direction. This is the direction. Well, actually, to be more precise, this is the direction. The direction vector is 40, 30. We know exactly which direction to walk to, but we don't know distance yet. So how far should I walk along that direction, right? So that's what we are doing next. All right, so 4 plus d1 times df over dx evaluated at that point is just 40. And the same thing here. 5, I think we decided to have start at the point 5 for y, plus d1 times 30. There you go. So now what I can do is I can substitute these two values into the original function, namely this one, and it will turn the function into a single variable in terms of d1. And let's just go ahead and do that. So the procedure at first seems kind of very intimidating, but after a while you will definitely get used to it. So f of x1, y1, we want to plug in these values, f of 4 plus 40 d1, 40 times d1, let's write it carefully, 40 times d1, comma, 5 plus 30 times d1. There you go. So I want to plug in these two values. So this is the value for x, and this is the value for y. So these are actually x1 and y1. right? So we just evaluated them in the previous step. So when you plug them into the function, you get 5 times. So x1 square, right? So I need to square that and then square the other one. So 4 plus 40 d1 squared plus 3 times 5 plus 30 d1 squared. There you go. So now decidedly, this is not a function of x1 and y1 anymore. This is a function in d1. And we know exactly how to optimize this function, how to find the minimum value of this function, right? So let's first expand it out. And then we can easily take the derivative and set it equal to 0 to find the minimum value for this function. So that will be, with a little bit of algebra, we have 5 times. So when you square that, it would be 16 plus 160, 320 d1 plus 1600 d1 squared plus 3 times. Inside the bracket, we have 25 plus 300 d1 plus 900 d1 squared. Now after you've multiply out with a 5 and with a 3 later on and add them together, so we have the coefficient in front of d1 squared will be 5 times 1600, which is 8000, and then from the second one we will get another 2700, so that will give us a total of 10,700 d1 squared plus. So the next one here, this product will be 1600 d1 plus 900 d1, that's 2500 d1 plus, and finally the constants would be 5 times 16 is 80, 3 times 25 is 75, 80 plus 75 is 155. So this is our new function in terms of d1 only, and now we want to minimize it as a function of d1. But this is just very easy business because this is a parabola. All we do is just take the derivative, set it equal to 0, and find the value of the step function, basically. All right, so when I take the derivative, so I get 2 times 10,700 d1 plus 2,500, and so that's the derivative of our function with respect to d1, and I set it equal to 0 to find out that our step function is minus 2,500 divided by 2 times 10,700. The zeros in the end cancel, so that's minus 25 over 214, which is roughly equal to, so you guys can find the value of the step function. But actually, let me just keep it as it is, well, or let's just calculate it, I guess. So on my calculator, when I do 25 divided by 214, that gives me 0.12. So what does that mean? Sorry, with a minus sign. Now, 0.12. So that's how far I should walk. But the minus sign tells me that, actually when I was, I just realized that the gradient always gives you the uphill. But because this is a minimization problem, we want to find the minimum of this function. We want to go downhill. So that's what the step function is telling you. Don't go uphill this direction. It's telling you to go that direction, in the opposite, the downward, downslope. So that's why we got a negative sign in front. But other than that, that's perfectly normal. Now that we know the value of d1, we can indeed find out what is the value of x1 and y1. So therefore, all right, x1 and y1 as a result comes out as 4 plus. So d1 is minus 0.12 times 40. And this one is 5 plus minus 0.12 times 30. Well, when you make the calculations, let's quickly do that. So I have 0.12 times 40 equals 4.80 plus 4. That will give me 8.80. And the second one will give me, oh, sorry, it was a minus sign. Sorry for that. 4.8 minus 4 is 0.80. Sorry for that. 0.80. There you go. And for the second one, it will give me 30 times minus 0.12. So that will give minus 3.6. And I add 5 to it. It would give me 1.4. 1.40. That's pretty much it. So that's x1, y1. But once I get x1, y1, the whole calculation will start all over again. So I need to go back. Luckily, the gradients are still the same. Sorry, these functions have not changed. Now I will replace these x and y with the new point, and I will find the new direction. Once I have the new direction, I will write an equation x2 and y2 in terms of d2s now, and then optimize again. All right, so let's quickly do it one more time, and then I'll show you how you can easily do it on Excel and for your assignment purposes as well. So now we are oops. Oh, I think I just shifted this inadvertently. All right. So second iteration. So for the second iteration, we're going to find x2, y2. So basically what we mean is we already learned starting from x0, y0. At this point, we walk down this slope all the way here. Now we need a new direction so that I can further walk down the slope. Do you guys see that? Let me probably do a different color. So we already walked through here. Now we are walking down the slope through here, and so on. Interesting to see that the machines, they do this all the time, right? This is how calculators are programmed, actually. All right, so like we did in the previous step, all I'm going to do is keep these gradient functions, 10x and 6y, and evaluate them at the new points, x1, y1, which is 0.80 and 1.40, right? And then we will proceed from there. All right, so let me go ahead and rewrite the functions. All right, so our original function f of xy, it was 5x squared plus 3y squared. We already calculated the derivative, which was 10x, the partial derivatives. And for y, that was 6y. And besides, we started with x0, y0 with the point 4, 5. And now we have our new point, x1, y1, which is the point, let's go back, 0.80 and 1.40. 0.80. It's kind of nice to see that we're approaching the actual minimum, right? The actual minimum, we know from the beginning that it was 0, 0. At the very early on in the problem, I mentioned that this problem was an easy problem, the 0, 0. The reason I'm doing all this is because I know the answer intuitively. So I know where the answer should be. So I want to make sure that I'm approaching that. In fact, let me do one more thing just to help everybody. So if you were to draw this, the contour lines for this one, it would look like this. So for instance, if this one was a 1, x would have been something smaller. So I think the contour lines would look like this, like little ellipses, all centered at this point 0, 0. So when I started at the point 4, 5, that was this point. Suppose 4, 5 is somewhere here. So what we did in the first step was to find that gradient. All we did is that tangent, the gradient. We started walking in that direction, and we stopped as soon as we hit this this tangency point. Does that make sense? And it turns out that the coordinates of this point is 0.8 and 1. Actually, I think that one was a minus sign in front. 4 minus 4.8. Yeah, sorry for that. This is a minus sign. Sorry for that. So the x must be a minus. Yes, yes, yes. All right. So this one came out as a minus. Another silly mistake, I guess. Minus 0.8. There you go. But it's clear, right? So we start at this point, 4, 5. And in the first, and this is our x0, y0. After one iteration of our algorithm, we are now at the point minus 0.8, comma 1.4. We are approaching towards this point, right? At that step, what we said is we are going to draw yet another perpendicular, right? A gradient, a new gradient, and we will get ever closer to our goal. We will keep walking on that direction, in this direction, until we hit the next tangent. So tiny, there you go, until we hit right here, at which point we will yet make another perpendicular 90-degree turn. So by making a lot of 90-degree turns, you approach ever closer to your destination. So right now in this iteration, I will try to reach to this point, x2, y2. This one was x1, y1. All right, so first let's evaluate these functions, the partial derivatives at the point x1, y1. And so 10 times x1 is just minus 0.8, so that's just a minus 8. And similarly for the second direction, so that one will be 6 times 1.4, 4, 6, 8, 8.4, I think. There you go. So we have our directions. Now we can go ahead and write the equation for x2 and y2. x2 is equal to y2 is equal to, so for x2 we will start at the point x1. We will walk along this direction by evaluated here, which we did already, so we will just substitute it right here. And we have the same thing for y2. We will start at y1, we will walk along this direction again. So this derivative gives you the direction where we're walking through. All right, so this is equal to, so x1, our starting point was, so this point here, minus 0.8 plus d2 times, and then this is the direction, minus 8, and this one is 1.4, our starting point, y1 is 1.4 plus d2 times, and the value is 8.4. There you go. So this is the direction again. So now that we know these values, we can substitute them into the function and minimize again. All right, so our function, we will evaluate it at x2, y2, and it will turn out to be 5 times x squared. So x, replace it with this monster over here, x2 squared. So that's minus 0.8 plus, sorry, minus 8d2 minus 8d2 squared plus 3 times 1.4 plus 8.4 d2 squared. That's it. So all we now need is to take the derivative of this function, evaluate it at with respect to, I should say, d2, and set it equal to 0 to find the value of the function. So it turns out that in order to take the derivative, unlike the previous case where I first expanded out, because the expression was nice in the previous one, here it was easy to expand it out. I'm going to take the derivative right away. So by using the chain rule that we all learned together, right? So that will be a good practice for our chain rule skills. The one thing is, I noticed that both of them are negative. Because I'm ultimately squaring them, it doesn't matter. Negative sign will just vanish. So I'm just going to assume these are positive, okay? It's the same thing. All right, so this is equal to 5 times. Taking the derivative, because it has a square, the 2 comes to the front. So we have 0.8 plus 8 d2. And then further, we need to multiply with the derivative of the inside, which is 8. Notice how I reduced the exponent by 1. Plus 3 times, 2 times, the exponent comes to the front. We just keep the inside, 8.4 d2. And then, again, a derivative, multiply with the derivative of inside, which is 8.4. That's it. So now we need to solve it, and this is a 1. This is not derivative, so maybe I should just get rid of those ones. We don't need them. All right, so therefore 0 equals, that's what I want to solve. 5 times 2 is 10 times 8 is 80 times, well, actually, you know what? Let me just multiply out this 10 with the inside, and then I can further multiply by 8. 10 times 0.8 is just 8. 8 times 8 is 64. Plus 10 times 8 is 80, times 8 is 640 d2. Oops, 640 d2 plus 6 times 1.4 times 8.4. Let me use a calculator actually. 6 times 1.4 times 8.4. So that one will give me 70.56. 70.56. Plus, okay, 6 times 8.4 times 8.4. 6 times 8.4 times 8.4 equals 423.36. 423.36 d2. There you go. Now we can go ahead and add these two parts. Plus 640. 1063.36. So 0, oops, 0 is equal to, so 1063.36 d2 plus the constants would be 7.56 plus 64, 134.56. And again, I need to find my step function d2 here. So as the length of the step, how much should I walk? d2 comes out as, let me just do the calculation, 134.56 divided by 1063.36. That's 0.13, again negative. 0, so telling me that I should walk downhill. It's reminding me to walk downhill here. So now I can go back to these and I can substitute d2, the value of d2 that I have just found. And so this way that I will be able to find the both x2, evaluate both x2 and y2. So again, minus 0.13 it is. So minus 0.8 plus minus 0.13 times minus 8. And that will be, and then for the second one, let me write out the second one as well before I proceed further. Times 8.4. All right, so let's calculate the first one first. So 8 times 0.13 minus times minus is just a plus, so it is 1.04 minus 0.8, so 0.24. You guys see how close we are getting to the ultimate destination of 0, 0. And then this one will be 0.13 times 8.4 equals plus minus plus 1.4, 0.31. Whew. So this is x2 and y2. So we are getting closer, inch by inch closer to our ultimate value of 0, 0. So we know that the global minimum is at this point, at the center, at the origin. But do you see how we started from the 0.45, our initial point, to that point 0.8, minus 0.8, 1.4, and now we are at this point 0.24, 0.31. All right, so let me just go ahead and stop this video here, and in the next video I will show you how you guys can easily solve this on Excel. Pretty easy actually, and all this work is pretty much redundant if you use Excel. It's good to know these steps. And I will try to use all these steps again, but Excel will do it way faster. All right, so hope to see you guys in the next video.